Identification of speech sounds in real-time MRI using DNNs. The ultimate goal of this ACCEL grant is to synthesize real-time MRI images that reflect dynamic changes within the vocal tract during speech production using DNNs. And this work is a step in that direction, which helped with implementing the right kind of DNNs for such a task, and also understand how best to use the real-time MRI data effectively for DNN training. The real-time MRI captured images of the entire vocal tract, examples of which are shown in the figure, as the subject who was lying inside the MRI machine spoke. In order to capture the dynamic movements within the vocal tract during continuous speech, each subject spoke VCV and CVC words that used 3 vowels and 19 consonants, which made a total of 22 sound classes. Effective DNN modeling requires large amounts of data and the right kind of model specific to the task. The more variability there is in a sound, due to co-articulation effects, for example, the more data we require to capture the characteristics of each sound. In order to model real-time data, DNNs that can capture temporal changes and encode sequence information would be required. In our experiments with DNN classification for the RT-MRI data, we found the attention-based encoder-decoder DNN using features extracted by the pre-trained VGG16 model to be most effective for this task. The results of the DNN classification presented in the table show high vowel identification accuracy, but the consonant accuracy isn't as good, which is to be expected since consonants have shorter duration and there are many more consonant type classes. However, the accuracy of 8 consonants of the CVC words was higher due to availability of more data. We compared these DNN recognition results with that of the human's perception of audio data as published by Weber et al. They published the confusion matrix for native English listeners, identifying sounds spoken by native English speakers in CV and VC combinations under normal listening conditions. The salient points from the DNN to human comparison, as shown by the confusion matrix here, have been listed, and as to be expected, there were many commonalities, but some differences as well. Overall, we found the sound recognition by the DNN from the visual representation, which is the RT-MRI, seems to mirror human audio perception. Also, more data would have been useful in improving the DNN accuracy. For our future work, we will be using accurately identified RT-MRI images from this study to train a DNN that can recognize audio data and synthesize the corresponding RT-MRI images. Thank you.